Hello, everybody. We'll just continue here. The December 2021 round USACO contest bronze level. The first question, known photos, we have explained in the previous session. We spent 1 hour there. Could not finish the other two questions. I promised I would do the other two questions. I did record them separately, but took probably too long for you to watch the video. So here today, I'm going to do it again, put the two questions together. Hopefully I'm going to finish not like in 2 hours. Hopefully we're going to do less than 1 hour. Some of the details I might leave it to the subsequent spring semester. Many students already in the momentum USACO class. So if you have done that in the fall semester, that's great. You have known what we have done before. And then in the second half of the calendar year, we're going to cover the rest 12 units. Actually, as I showed before, right, we're going to mention before, we would cover every round of the USACO contest actually in the Jan round, which would occur at the end of this month, Jan 28th through Jan 31st. We would do that in the first week when we resume the spring semester. That would be Feb the 5th and Feb the 6th. We're going to spend 2 hours for the bronze review. Should be the Feb the 5th Saturday. All right, okay, so let's talk about the question 2 and question 3 in the December round contest. Question 2, that's the air conditioning. We're given two arrays. One array is the final temperature here. This is the temperature that we need to reach the final, and then this is the initial temperature that we want to, we have. The goal is to lift the temperature from the initial or lower, so that they would at each location, the two arrays would be the same. When we lift or lower the temperature from the second array to the first array, we could do either individually or we could do that in an interval. And we want to find out what is the minimum number of the lifting or the lowering we need to perform so that the initial array would be the same as the final array. So many of you try to work on the question using the initial and final. Actually, we can do a different approach. We can define a vector, an array that is f minus I, the final temperature minus the initial temperature. So that's the difference. This is actually common, right? If you have done physics, that's the final position, that's the initial position. So this D is the displacement. Okay, so now you can change the question from reading the two arrays to reading just one array, D. Of course, right, when we read them, we're going to just do the difference and we're going to just work with one array of size N. N is given at the beginning of the input. All right, let's take a look at this sample here. So if we do the difference, so the first one should be 0 here, 1 minus 1, 5 minus 2, that's 3 here, 3 minus 2, that's 1, 3 minus 2, that's 1, 4 minus 1, that's 3 here. If I want to make this array D to be all 0, this one is already 0, don't worry about it. Now we're looking at this part here. If I want to make all of them 0, then I should decrease the values, right? So first interval I'm going to decrease would be say 3, 1, 1, 3. Every value will decrease by 1. So that's one operation. So this would be 0. Don't worry about this one. It's already 0. So this would be 2 and 0, that's 2. Now, this is 0. Don't worry about it, right? We're going to focus in this interval. Well, this interval has only one element. Every time you're going to lower by 1, so it will take 2 times, 2 moves to make this 0. This one again would require the lowering by itself. Again, this interval has just one element, so this will take another 2 rounds. Suppose it's 2 and 0, 0, 0, 0, and 0. So we have achieved the goal, so that the D array, this displacement or the difference array, now every element is 0. And it took us 1 plus 2 plus 2, so that's 5 times. Notice here, this one, we have just one block of the numbers. Suppose I have another 0 and have, say, a negative number and then 0. The same idea applies here. So you're going to just look at the intervals of positive integers in this array D and look at the block of the negative integers and how we decide the blocks depending on the zeros. So we're going to use the 0 to partition the array D into different blocks. The blocks of the positive numbers and blocks of negative numbers, and each block will be processed independently. This is one idea of what we call the greedy algorithm. Sometimes you need to convince yourself this idea works, will give us the correct answer. Well, this is different from math. You don't have to have the complete proof, the rigorous proof. Just convince yourself. If you don't find major mistake or flaw in the reasoning, then just go for it. The criterion for USACO failure or success, right, is whether you pass the test cases. You don't have to provide the proof. So this is one example of the greedy algorithms. Actually, we would also address the greedy algorithms. Actually, unit 20, we're going to address greedy algorithms. It is not just for the bronze level. Actually, it is a very important tool for all the levels: silver, gold, platinum. All right, so our idea is to convert the 2 arrays into one array D. And then for this array D, we're going to partition the elements into blocks of positive integers and blocks of negative integers. For each block, we're going to process, see how many times it would, how many steps it requires to bring all the numbers 0. Okay, so we have seen this here. Say the example 3113. If you put the number in this way, so this is block of the numbers. I'm going to visualize the numbers, right, using the Y value, like the histograms. So here you have a value 3, here you have 1, and you have 1, and you have 3. Suppose you have another 4 and you have another, say, 10. See how many times, or how many times of the lifting or the lowering you need to do. Well, this one, right, since D is positive, you have to bring it down. Or we can say start from 0, how many times you need to make this from 0, 0, 0, right, all the way to this 3, 1, 1, 3 here. The process would be the same. You will lower this down, or you raise this one, would be the same. So suppose I start from 0, because, right, every block of 0, you have to start from this 0 here. So raise from 0 to 3, you need 3 steps, 3 moves. This one is lower than the 3. As you raise this 0 to 3, you can also raise this to 1. And then, right, this one is higher than this one, then this will just go along. This one still stay here. It stays here. So this one actually requires no extra move. When you move this to from 0 to 3, it already satisfies the requirement raise this one from 0 to 1. So this one will, contribution to the total count would be 0. This one is the same as this one, so also the contribution would be 0. 3 is higher than 1. The previous block, the interval, right, when you lift up, will stop here. Even though this one is high, you cannot say the interval go beyond, because if you try to lift an interval like this one, then if you do 3 times, then this number will go above 1. So your interval would go at first, right? Leave all the 3 numbers raised to 1 here, and then you're going to have the interval just by itself raise 2 extra steps. Okay, anyway, the interval will just stop here in the previous, working with first 3 numbers here. This 3 would require another interval. Okay, when you did 1 here, that's fine. We're going to put everything 1 here, but this 3 is 2 units higher than the 1, so it will require 2 extra moves. 2 extra moves to go beyond this 1 to 3. The same argument, right? 4 is 1 unit higher than 3, so this one requires 1 extra move. This one requires 6 extra moves. Suppose this one is say 8. Again, 8 is lower than 10. When you raise this to 10, you have already raised this unit to 8. So this one will be 0. The contribution to the total count. So you see the pattern. If a number, say position J, if position J is less than the previous number, D at J minus 1, then this one, the contribution is 0. If this J is bigger than the previous number, then you're going to add the difference between the 2 values. This is dj minus d at j minus 1. This number should be added to the total count, the count of the moves. Okay, that's for the positive blocks. The negative blocks would be processed the same way. Actually, you can do another a small trick, right? We'll say take a negation of every number and then just use the same process, or actually write a helper function to count the number of the moves I need for this block. Suppose that's a 0 here, there's a 0 here. All right, so let's try this. Okay, I tried to make this short. Clear everything. Now I'm going to write for this one, and then for the other one, I'm going to just walk you through. Okay, so here condition, I'm going to write conditioning. Since I have this already, I'm going to write this, say 2. First, I'm going to read n. So that's the number of the integers, or the length of the integers. I'm going to do the array D. J goes from 0, J less than n here, J plus plus. Initially, I'm going to read this one. So this is actually the final temperature, right? Final temperature. Okay. And then I'm going to read the initial, but I don't want to save 2 arrays. Actually, I'm going to just do the difference. So here, dj should be subtracted from by the initial condition, initial values, right? Temperature. So here, minus equals in dot next. So this becomes the difference of the temperatures. Okay. Now, I want to find out the total count of the moves. Okay, so I want to find out the blocks of the positive integers and also the blocks of the negative integers. Count, so total should be 0 here, and hopefully this should be an integer range. If this one does not work, right, you might need to think this should be a long integer. What is the range of the integers? All the numbers are in the range. What is range? Actually, it did not say so. Okay, doesn't matter. So we're going to try int, and if it works, then it's fine. Otherwise, one potential problem or bug, right, may come from, say, total would go out of the range of integer, then just change that to long, should be okay. All right, so we're going to try for the blocks. Say x starts from 0, while x is less than n. Okay, if dx is 0, what do I do here? When this entry is 0, do nothing, just say continue. Okay, otherwise we're going to find out a block. So dx, if I continue this here, if I reach this one here, otherwise, right, I would skip the rest of the iteration. If I do have to execute the commands after 918, then dx is not 0. Either it is positive or negative. Okay, so here we're going to find the interval. So d at x and all the way to y, this would be all positive or negative. Y would be the biggest index so that this block would contain all positive or negative. All right, so here I'm going to say y would be x here. I'm going to do another one. So this is a trick that we have done a couple of times, actually. I think in the first question, we also used it. This is a trick that we have seen in the question, like finding the clumps, right? You can find out the block of the integers that are the same, right? We have seen this one. Actually, last time I've also mentioned finding the clumps. So here the clump is not a block of integers of the same value, but here the number of the same sign. So the same trick. So while y is less than n, and also dy and dx would have the same sign. What do we do? I'm going to increase by 1. If the current y position, dy and dx, the product is positive, that means they have the same sign. And this is guaranteed, right? This would be not 0. Because if dy is 0, then this would not be positive. Maybe I should try this one here. Use this. Okay, now I'm going to try to the right of x. Y is at least x plus 1. Now, when this part is done, y would be the first index, so that dy and dx would be different sign. Either dy would be 0 or dy would be the negation, the sign of dx. Okay, so now we're going to work on this. So if dx is positive, I'm going to count the number of the moves to bring all the zeros, all the entries, right, in dx to 0, or start from 0, bring it to dx. Okay, so I'm going to say the total should be increased by, let's say, count. This would be array A, D here, and then start from X and Y. Okay, I'm writing another function here. So this would be static int count. This would be the integer array D and the low, and this would be the high. And I'm going to have return 0, so it will not complain. So what I want to do this one is I count the number of moves, so that I'm going to bring the array D between X inclusive, high exclusive, make all the numbers to 0, or bring from 0 to this D. What is the number of the moves to raise from 0 to D in low and high. Low is inclusive and high is exclusive. The same thing, right? The number of moves would be the same. You bring down D, all entries to 0 in the interval from low to high. Okay, so that's the part when dx is positive. If dx is negative, I can do this here. So for okay, z goes from x here, z less than y, z plus plus, and we're going to take negation of, so dz would be negative dz. Okay, and then do the same thing here, total plus equals count dx and y. And next time, right, I have done this x through y here. The part from x and x plus 1, x plus 2, right, I've processed, so don't process them again. So I'm going to say for the next iteration of while loop, x will take the value of y. Since I have processed the part from x all the way through y minus 1. So next time, if I want to find out the blocks, I should start from y. Okay, at the end, I'm going to just print the total. Okay, so this part is not too bad. Okay, if I want to remove these to make it more compact. Okay, this part should be clear. Now what we need to do is fill the blank for this one. Given us an interval in this array D, try to find out the moves so that we're going to either raise from all 0 to this array D over this interval, or start from D and bring to. Okay, so now we're going to say the return value is X, and of course, right now we're going to say return the RET. Okay, what I have done here, right, we're going to assume this one is the interval. I mean, the array over this interval should be positive. If it's negative, we have made negation. So we're going to assume this D over this interval is positive. Okay, so here we say the previous position is the difference is 0 because, right, we start from D at low. Actually, it's not 0. D at low is actually positive. So X starts from low, X less than high, plus plus. This time I need to have a block. Okay, so here, if D at X, if it is bigger than the previous, then we need to increase, right? The difference between dx and the previous one should be added to the total count. And previous should take the value of dx for the next iteration. Okay, so here, right, we're going to start from low and less than high. And then when we're done, we should have all the contribution from every position counted to the answer returned here. And when we're done, just return this one. So we're going to call the function twice. Not twice. The number of times we see the blocks. Every block, we're going to call the function once, but it's guaranteed, right? All the blocks, they do not overlap. So in essentially, every entry in this array D would be processed once. So even though we do have the loop here, one layer here, another layer here, so it looks like that's 2 layers. Actually, every entry is processed once, and you this while loop is independent of this one here. So anyway, we do have another loop here, but again, this loop looks like the 2-layered, but essentially everyone is processed once. So the number of iterations for this part from 917 all the way through 934 actually would be proportional to the number of elements in this array, that is n. So using the terminology that we're going to get familiar, the big O notation. So this one, the number of operations would be big O n. That means would be proportional to n. If n gets bigger, then it would number of operations will be bigger. In this case, n is what is the size of n? Oh, here n is at the most 100,000. So we're going to run this one maybe 2 times, 3 times, 10 times of n. So if n is 10.5 times 10, that's 10.6. We have said before, right? If your number of operations is less than 10.9, a count of the operations could be addition, subtraction, multiplication, division, right? Or sometimes even square root. All these operations, add them together, the count. If it's less than 1 billion, very likely you should be able to finish the calculation. Okay, since n is 10.5, you multiply a factor or constant multiply, right? This number could be 5, could be 10, whatever, right? So even you do 10, that's still just 10.6. That would be much less than 10.9. So we would be able to finish the calculation. Many of you have experienced the TRE, the time limit exceeded error, especially for the last 2 test cases. That is because you spend time that is much bigger than the 10.6. Many of you have shown, right, this one would be a 1 layer n, and you have another layer n, or n over 2. So that's n squared. When n goes to 10.5, n squared would be 10.10. That's 10 billion. You say, I've done the second layer, which is n over 2. So that's still 5 billion. 5 billion still would be much bigger than this threshold. So it's not surprising that you're going to see the timed out error. Okay, this is actually a different style from before. I also mentioned the trend, right? So previously, you don't have cases, test cases like this, or the n, right, would be big enough, or I mean, small enough so that if you do the brute force way, you should be able to get all the credit from the test cases. But this round, the style has changed. It's not too big, right? So even you try the brute force, you can still get 8 out of the 10. So 80% of the credits, that's enough to get the promotion. If you can claim this percentage for every question, of course, right? Sometimes you cannot finish, all 3 questions with the high percentage. So you have to, for the questions that you know how to do, try to pass them as, pass as many cases as possible. For those, for the, the question that you don't know what to do, or don't have the confidence, then you try to pass the simple test cases. All right, so here, let's try this one here. Since I have the test cases downloaded, right? I have here. So let's run this. Okay, you can see here, right? I have the conditional 2. So run J conditioning 2. There's a mistake. Something is wrong. It did not finish. Let me just run the test case here. Let me see what went wrong. This part should be fine. Oh, I see. No. Before I continue, I need to increase X, right? Otherwise, when I see 0, then it will get stuck all the time here. Now let's run this one here. Yes. Is it 5? Yes. Okay, let's try this again one more time. Okay, good. Okay, they're all correct. Not too bad, right? Okay, everybody. Now let's go to question 3, walking home. This one actually is a little bit different. N is not too big. N is the size of the grid. n by n, this is a square square grid. We need to go from the upper left corner to the lower right corner. For each sub-test case, we need to go this one here. We always start from the upper left corner, this one, and then need to reach the lower right corner. And then for each sub-test case, we have the restriction, the number of the turns we can take. This K is the number of turns. You do have the freedom at the beginning, right? Upper left corner, you can start facing east or you can face south. So for example, right, if you can only do change the direction once, then you can say, I can go east at the beginning and then reach the last column and then turn south and see whether I can reach this one. Or I can start facing south when I hit the bottom row and turn east. So that's just one time of the direction change. You can also change in the middle when K is 2, or you can change 3. You can do zigzag, zigzag, zig. That's facing east first, right? Turning, that's once, twice, and 3 times. So facing east, turn, turn, turn 3 times, or facing south first, turn, turn, and turn. So you can do this one when K is at most 3. I think that's what the question has here. So for all the test cases, K would be either 1, 2, or 3. Here I'm going to show a technique that probably would be better than the brute force way. You can actually, I would strongly recommend you follow your instinct. You're going to say, I'm going to do turn once, turn twice, and turn 3 times. But here I'm going to show a trick. It's called dynamic programming. You know, right? Many say, okay, I don't know that technique. Actually, you would not get to use this technique until you're at the silver level. And then this DP is the most important technique, or I would say the most frequently used technique for USACO contest, especially at gold and platinum. And we had the statistic, right? At gold level for the past 6 seasons, about 1/3 of the questions that you use DP to solve. So that is the most frequent technique. All right. So you say, I don't know this one. Actually, some of you, right, have been in my Java class. Actually, we did this one even in the introductory class. Okay. Just bring your memory back. Remember that the Fibonacci sequence, Fn is defined to be Fn minus 1 plus Fn minus 2 here. You could do this one recursively. Actually, right in the recursion unit that we have done here. The recursion, we have done the Fibonacci sequence. One of the questions would be, actually it's not here. Okay, in the summer camp class, we did cover that one anyway. So here, if you want to find out say 10, you need to find out F9 and F8. When you need to find out F9, you need to know F8 and F7. So this would be recursive. That's a perfect example when n is small. But when n gets bigger, then we don't want to try this recursive way. Rather, we're going to do the DP. That is, well, actually still recursion, but we're going to remember the results from the subproblems where the input sizes are smaller. So that's basically how you describe DP. All right. How we did this one here, we said we're going to implement an array. So this is 0 and 1, 2, 3, 4. So if you know F1 and F2, you just get F3, right? Just add these 2 numbers together, then that's F3. If you have F2 and F3, then you can find out F4. So basically, right, you can continue the fashion until you reach, say, n. So this would be much simpler. Right? If you want to find out Fn, I start from F1, F2. normally, right, you would get these values. If you want to find out the Fibonacci sequence, give me the first term, give me the second term, then you can find out any the term, right, at any position n. So this actually, right, each time I need to find out this one takes one addition, another addition. So here I need n additions. So that'd be much simpler. You don't have to do the recursion that will require exponential time. When n is small, that's fine. But when it's say big than say 30, then you'll be in trouble, right? Because this one actually the number of operations go exponentially 2 to the power of n. When n is 30, 2 to the power of 30, this one is roughly 10, 9, a billion, right? This is the number that we have said many times, a threshold, a magic threshold. If your number of operations less than this number, you're going to finish. Otherwise, we're not going to finish this. Okay, so when n is bigger than 30, you don't want to try this, the simple recursion, right? So this is the idea we have tried. You can check your notes if you have them, right? We can finish this fn. Fn could be 100, could be 1,000, could be a million. We can still finish this very fast. This one you're going to do much, much slower. Okay, so this technique would be used to solve question 3. So I'm going to just go through this implementation. Actually, it's not too long. This is the brute force way. If you want to try to implement it, and then I'm going to show this here. T is the number of subtest cases. We're going to work for each subtest case individually or independently. N is the size of the grid. K is the number of the direction changes allowed, the maximum number. The grid, we're going to save them into a character array of size n by n. Read it. Every time you read one row here, and you can convert into the character array. So you don't have to write another loop, just say use the function toArray character, and this will be assigned to this grid R. Grid R is itself another array of one dimension. Now we're going to use the technique. You're going to feel this one, maybe at the beginning a little bit difficult to do, but after a while, calm down. This would not be that hard or weird. It's actually kind of, it does make sense. Okay, we're going to have an array here, 4 dimensions. Okay, don't be afraid. Okay, the first 2 dimensions will be the number of rows, number of columns of this grid here. And then the third dimension would be the number of the turns you have done. So when case 1, you have done 1. Well, here I'm going to use x, right? When x is 1, you have turned once the direction. When x2, you have turned twice. When x3, you have turned 3 times. Okay, and then this one, we're going to record the current direction. Since there are only 2 directions, either you're facing east or facing south. So here, facing east, I'm going to say that's 0. Facing south, that's 1 here. So the 4th dimension only has 2 values. So if you want to find out the number of the elements we need to store in this array, n times n, that's n squared times k plus 1 times 2. Since n is at most 50, so here this the storage for this array, right? So n squared, that's 50, and that's another 50. K is at most 3. I'm going to multiply 4 times 2. So that's not too bad, right? So that's 200 times another 100. So this is 2 times 10, 4. Number of elements. Each element takes 4 bytes. So that's 8 times 10, 4. So this is about 800 K bytes. Actually 80 K bytes, not 800. So this is 0.08 megabytes. And how many bytes we can have for each USACO submission, right? We said we can have up to 256 megabytes for each submission. So that's tiny. Don't worry about say, okay, this array has 4 dimensions. Do I have enough space in the memory? Don't worry, it's okay. All right, the first 2 positions we need to assign. So by default, right, every element in this array should have default value 0. But these two positions, we're going to say it's 1. Why? We have at position 0, 0, the upper left corner. This is how many, this array, right, record the number of ways to reach the position here, RC, while having changed the direction X times and then ending at direction Y. How many ways are here? Since we're already here, right? There is one way to be here, one way to be here. At position 0, 0, having changed direction 0 times, facing east, facing south. Okay, these two would be assigned to 1. All other entries in this array W would be 0 at so far. All right, so far so good. Now we're going to move on to the this loop here. The whole thing would be in this loop again. Since we have 4 dimensions, we should have 4 layers, or actually the last dimension, right, only has 2 numbers. We're going to just write it explicitly. So we're going to have 3 layers. So the R layer from 0 through n-1, C layer from 0 through n-1, X layer, we're going to go from 0 less than equal to K. How many times we have changed the direction? So could it be 0 all the way through K? Since K is at most 3, so here this layer would give us at most 4 iterations. So n times 4, right? That's not too bad. Okay, so here this part is if currently we are at this position RC and having changed the direction X times and facing 0. If this entry is positive, that means we can reach this position with the configuration. If this entry is 0, that means we cannot reach here. That means, right, it is by default 0. We cannot be there with that configuration. If it's positive, we can arrive here with X turns still facing east. So we have 2 choices. Either we're going to say continue the east direction, or we're going to turn. If we continue the east, make sure we can go to the position on the east. That means, right, R would still remain the same, but C would increase by 1. So suppose C plus 1 is less than n, that means it is still within the grid. Then the number of ways to reach this configuration should be increased by the number of ways we have been at RC. Maybe there are some other ways to reach this RC minus plus 1, but this is one way to reach it. So we're going to say increase the number of ways to reach this R comma C plus 1 X 0. Okay, so here X would be the same because we continued direction east. We did not increase the number of turns of the direction. But if we do change the direction, okay, at this location, we have changed direction X times, but to go to south, R plus 1C, right, we have also recorded 1 more turn of the direction. Okay, so this has to be satisfied simultaneously. You want to go south. So if you are at this location, this is R and C here. South, you're going to do R plus 1 and C. R plus C is positive. Why would do R plus C positive? Oh, if it is 0, you don't want to waste that one, right? If it is R plus C is 0, that means R is 0, C is 0. You don't want to waste that one because it's already done there. And also R plus 1 is less than n. You don't want to go out of the grid. Okay, this entry must be a dot. Dot means you can be there. And X plus 1 should be less than or equal to K. If it's right, I have been here already to reach the location RC. I have changed direction 3 times, right? I was going this way here to reach this. I was here at facing east. If I turn 1 more round, if this is already 4 times of changing, then this is not allowed. So all the conditions have to be satisfied, then we can do this. Okay. Then If we are at the location RC facing south, then either we can continue the south here or we're going to change to east. That means we're going to increase X by 1. So here, one more turn. Okay, when we finish all the iterations for all the positions RC, all the number of turns X, and also facing east or facing south. When we're all done, we're going to count how many ways you can reach the location n-1, n-1, right? That's the lower right corner. We don't mind out how many times you have turned, as long as this one is no more than k, and we don't mind what is the final position you're facing. So here I'm going to run the loop, right? X will go from 0 through k, including k. Y would go from 0 and 1. All these would be valid ways to reach the destination, lower right corner. When we've done this one, we're going to print the answer. And T is the number of sub test cases. Every time you're going to decrease k by 1, so we're going to process each sub test case. And then when we're done, we should be able to just close, and then should be okay. So here, it will be pretty fast. Here, Bing, I'm going to do walking to. Yeah, and then they should be correct. Okay, so. All right, back to what we said at the beginning, right? The style of the USACO contest has been slowly but steadily changing. Each level, I think it is getting more challenge. So in the spring semester, the second half of our USACO bronze class, we try to also meet the demand. This is actually consistent with our prediction, our expectation for the USACO contest. It will just get more competitive. One obvious reason is a lot of students now joining this contest. So to still maintain roughly the same number of people get promoted, right, then the percentage would get smaller. We hope, right, we're going to get more levels. So you're going to have more rewarding. Every time you make progress, you should be rewarded, not to be frustrated, right? I've been at Gold for 2 years, still working on this to get the final promotion. Yeah, that is common. But if, right, there are 10 levels, probably you're going to every round, you're going to see promotion 1 or twice. So you will be happy, and you can have more interest to work hard. So we hope that will be the case. Anyway, platinum was added in season 2016. So if we have more levels added in the subsequent seasons, that would be actually, will not be surprised at all. Okay, so in the spring semester, we're going to provide a transition, a smooth transition from the entry bronze level to the higher or advanced bronze level. And this advanced bronze level should be kind of close to the entry level of the silver level, right? I also mentioned, said before, after you pass the bronze contest, even you get the promotion, does not mean, right, overnight your skill level, your the rating, right, would have a quantum leap, a jump. That's not the case. You're still the same person, right? Maybe you're feeling better, more experienced, but not to show, right, bronze is 0, silver is 1. That's not the case, 0 to 1. Or from 1 to 2, that's not the case. So be patient. So in the spring semester, we're going to go through the techniques, the questions that will be more challenge than the fall semester. But you should be more confident that when you look back for most of the bronze questions, you should have the confidence, even though you don't say, okay, I can finish this one within, say, 20 minutes, 30 minutes. but you should have the confidence, say, okay, give me enough time, an hour, 20 minutes, I would be able to finish it. With the confidence, then you're going to do much better. And of course, right, this will also give you the confidence when you start the silver level training. From the silver level, then the efficiency of the code would be the key. We don't worry about other issues. The efficiency of your code is the only concern for the user context. All right. Okay. I know, right? Some of you may still have, confusion of the questions or some of the details. We still have about 3 weeks before the Gen round, so just work hard. And if you still have any confusion, right, feel free to let me know. We will be able to try to answer the emails, the messages. A group of our TAs would be very happy to work together to provide the support. So with this, I'll stop here and wish you good luck in the Gen round. And we're going to see you at the beginning of February when we start the spring semester. All right, bye.